In today's lesson, we'll talk about one of the most important constants in mathematics, the Euler's number E. The number E, known as the Euler's number, is a mathematical constant approximately equal to 2.71828. It can be characterized in many ways. It is the base of the natural logarithm. It is the limit of the quantity 1 plus 1 over n raised to n as n approaches infinity. It is an expression that arises in the study of compound interest, and it can be calculated as the sum of infinite series, which we are going to derive today. This constant was discovered by the Swiss mathematician Jacob Bernoulli while studying compound interest in 1683. In 1731, Leonhard Euler introduced the letter E as the base for natural logarithms. Euler started to use the letter E for the constant in an unpublished paper on explosive forces in canons in 1727. The first appearance of E in a publication was in Euler's Mechanica in 1736. Here are some facts about the known decimal digits of E. In 1690, Jacob Bernoulli computed the number E to one decimal digit, that means 2.7. In 1714, Roger Coates computed the number E to 13 decimal digits, while in 1748, Leonhard Euler himself computed the number E up to 23 decimal digits. And the famous mathematician John von Neumann, using the ENIAC computer, computed the number E in 1949 up to 2010 decimal digits. In 1961, Daniel Shanks and John Wrench computed the number E up to 100,265 decimal digits. And later on, Steve Wozniak of Apple Computer computed the number E in 1978 up to 116,000 decimal digits using the Apple II computer. Since around 2010, due to the proliferation of modern high-speed computers, the number E has been calculated up to 8 trillion digits. During the emergence of the internet culture, individuals and organizations paid homage to the number E. For example, in 2004, Google announced its intention to raise $2,718,281,828 US, which is E billion dollars, rounded to the nearest dollar. In today's lesson, we are going to bridge the connection between the Bernoulli equation for E to that of Euler's infinite sum for E. You would like to see how Euler himself computed the first 23 decimal digits of the number E in 1748, and then we will see how to transform the infinite sum further to quantify our error from the true value. So at this point, we are now ready to prove that the limit of the quantity 1 plus 1 over n raised to n as n approaches infinity is equal to the summation from n equals 0 to infinity of the expression 1 over n factorial. Remember that this left-hand side expression is how Jacob Bernoulli discovered the value of E. And this right-hand expression also is how Leonhard Euler computed the first 23 decimal digits of the number E. So we would like to establish the connection that the left-hand side is indeed equal to the right-hand side using acceptable mathematical rigor. So what does this mean? This right-hand side means we are summing up the expression 1 over n factorial, but our n would iterate from 0 to 1, 2 factorial, 3 factorial, and this will continue forever because n is from 0 to infinity. So this is an infinite sum. So what we want to do is show that this left-hand side would become like this. So let's implement our plan. So to start, let's remember this binomial theorem. So when you have a binomial x and y, and that is raised to n, the expansion of this binomial x plus y raised to n is given by this formula. It's the summation from k equals 0 up to n of certain coefficients, and the first term here is x with an exponent of n minus k, and the second term is y with an exponent of k. But k is from 0 to n, so it's iterating from 0 to n. So the value of this n and k would be moving from 0 to 1 to 3 to 4 up to n. And this coefficient part is the combination formula. So we interpret this as n choose k, or the combination of n objects taken k at a time. To apply now this binomial theorem to expand this expression 1 plus 1 over n raised to n, then that would result to this expression. Our first term is 1, so that's our x here, and then copy n minus k Our second term is 1 over n. That's our y. That should be this y here. So you have 1 over n. All the rest are copied. The next thing that we have to do is evaluate this part. So this is now the result. The combination nk is now n0 because our k starts with 0. And then this is our first term. Just copy that. Then our n is n, but our k is 0. So you have n minus 0. Copy the second term, 1 over n, and replace this k with 0. That's the first term. Then let's move to the second term. So from k equals 0, then k equals 1. That's why you have now the 1 here in place of this k. Then you have n minus 1 instead of n minus k. And instead of this k exponent, you have this 1 exponent. Then we iterate. We move to the next counting number. So you have 2 and then n minus 2 and 2. All the rest are the same form. Then move to the next counting number 3. So you have here n minus 3 for n minus k, and you have the exponent 3. But this is from k equals 0 up to n. So we do not know the value of n. What we know is n is approaching infinity. So the number of these terms would be extending without limit. We do not know how many terms there are. What we know is there are a lot of them. And our goal is to find what is the sum of those infinite terms. Isn't it crazy? Finding the sum of infinite terms. How can you find the sum of infinite terms? You cannot even know how many terms there are. But there is a mathematical way to do that. Now, let's continue. This part here, the combination part, we can evaluate using the formula for combination, which is this part. The combination of n objects taken k at a time is equal to n factorial over k factorial times n minus k factorial, which we already derived in the previous problem. So all we have to do is apply this formula. So for this part, we now have n factorial over our k is 0, then the quantity n minus 0 for the quantity n minus k in the formula. And then don't forget the factorial notation. Then copy this part. Copy that part. Then evaluate the combination of n objects taken one at a time. That is now this value, n factorial over, instead of k factorial, we have 1 factorial now, and then we have quantity n minus 1 factorial. That's how we evaluate the second one. And then evaluate the next combination. That would be this third part, and this combination would be evaluated this way. All these other parts are just copied. We will find a way to simplify this part. So let's start with this one. You have n factorial over 0 factorial times n minus 0 factorial. Just copy n factorial. What is the value of 0 factorial? By definition, 0 factorial has a value of 1. N minus 0 is n, so you still have n factorial. And we can divide n factorial by n factorial, and the result is 1. So therefore, this part here is 1. And you now have 1 times 1 raised to n minus 0. 1 n minus 0 is n times this part, 1 over n, which is also raised to 0. The number 1 raised to any number, whether it's 1 to the first, 1 to the second, 1 to the 100, if you multiply 1 by itself, the result is always 1. So even if n is a very, very big number, you raise 1 to that big number, the result is still 1. So we still have 1 here. I copy this 1 here. And here, any number raised to 0 is also 1. So therefore, 1 times 1 times 1 equals 1. This part here is equal to 1. That's now the value. I copy the limit as n approaches infinity. And then the first term, the entire thing here, this entire thing is equal to this 1. Then let's compute the second one. So now let's compute this part. So what's the value of this part? So you have n factorial over 1. What is 1 factorial? 1 factorial is 1. And then you have n minus 1 factorial. N minus 1 factorial. Now the technique here is, if you have n factorial and if you have n minus 1 factorial here, you can expand this to n times n minus 1 factorial. Because remember, if you have 5 factorial, that means 5 times 4 times 3 times 2 times 1. But if you have 5 factorial over, let's say 4 factorial, you do not have to expand this anymore because you have a 4 factorial here. So what you can do is, instead of expanding that part, you can just write 5 times 4 factorial, because 4 factorial is 4 times 3 times 2 times 1. And you have a 4 factorial here that you can cancel out, and so you will get this 5. We are going to use the same reasoning here. What we are going to do is, we'll be able to cancel out the n minus 1 factorial and the n minus 1 factorial. So we are left with n. So this part here has a value of n. So if you want this times that, then we'll have n times 1 raised to n minus 1 times 1 over n raised to 1. Notice that if n is a very big number, n minus 1 is still a big number, but 1 raised to any number is still 1. So this part here has a value of 1. So you have n times 1. And any number raised to 1 is still the same number, so we just copy 1 over n. And you can cancel out the n, and so what's the result? 1 times 1 equals 1. So this entire term, when evaluated, is equal to 1. And that is now this value. So the first term was this. The second term when evaluated is this. The next part is we are going to evaluate. What is the value of n factorial over 2 factorial times n minus 2 factorial? Again, the same technique we are going to use. We just evaluate n factorial to n times n minus 1 times n minus 2, but stop at n minus 2 and then put the factorial sign. That way we'll be able to cancel out the quantity of n minus 2 factorial. So we are left with n times n minus 1 all over 2 factorial. And then let's evaluate this. 1 raised to any number is 1. So basically this part is just 1. And the other part is 1 over n raised to the second power. So what we have is n times n minus 1 over 2 factorial. 1 raised to the second power is still 1. And n raised to the second power is n squared. So that's what we have. And simplifying this, we have common n here. So you have n at the bottom. We are left with n minus 1 over 2 factorial times n. Now this part, we can rewrite further because later on we are going to evaluate the limit. We want to write that in the form a number, let's say 1, and a number over n, because if you have a number over n, as n becomes bigger and bigger, then the value of this would approach 0 when we evaluate the limit. Then we'll be able to have a constant as the value of that limit. So we are going to write that in the form a constant minus a constant over n. And this is how we are going to do that. Let us separate this 2 factorial, 1 at the top over 2 factorial. And you have n minus 1 over n. Notice that if I divide n divided by n, so this n divided by n, what's the result? N divided by n is 1. And 1 divided by n is 1 over n. So in other words, this value here can be written as 1 over 2 factorial times the quantity 1 minus 1 over n. But this form is easier to work with when we evaluate the limit as n approaches infinity. So that is now what we have here. The value now of this part is this expression, 1 over 2 factorial times 1 minus 1 over n. So for the next one, you have n factorial. Notice that you have n minus 3 factorial here. So we already know that we are going to expand this way. We stop at n minus 3 factorial because we can cancel that with n minus 3 factorial at the bottom. And then you still have this 3 factorial. So cancel this out. What we have is n times n minus 1 times n minus 2 over 3 factorial. This part here is the evaluation of this combination. And then the number 1 raised to any number is still the number 1. So don't worry about this part. That's 1. Any number multiplied by 1 is still 1. So just ignore that part. But you have here 1 to the third over n to the third. 1 to the third over n to the third. So at this point, we need to simplify the top. So if we're going to expand this, you have n squared minus n. So I just distribute this times n minus 2. And our divisor is n cubed. This n cubed we can split as n squared times n. N squared times n is still n cubed. So we can split that as n squared times n. Now, why I'm doing that? Because as I've said, we want to write this in the form 1 minus 1 over n. Notice that n squared divided by n squared, this one divided by this is 1. N divided by n squared is 1 over n. So we put 1 over n. Here, n divided by n is 1. 2 divided by n is 2 over n. This is the form that we want because we can easily find the limit of this as n approaches infinity. So therefore, this part here is equal to this one. Let me write that down. So this value is equal to that, but don't forget that we still have the 3 factorial at the bottom. So we put the 3 factorial and the 3 factorial. Now, this one can also be written as 1 over 3 factorial, this 1 over 3 factorial, and then this expression 1 minus 1 over n times 1 minus 2 over n. The evaluation of all of this would now be the limit as n approaches infinity of 1 plus 1 plus 1 over 2 factorial times 1 minus 1 over n plus 1 over 3 factorial times 1 minus 1 over n, 1 minus 2 over n plus and so on. So this part here is now evaluated this way. But the value of n here iterates from k equals 0 to n, where n is approaching infinity. So the number of terms here would be extending without limit. There are still a lot more other terms. Now let me rewrite them here. So this is the expression that we are trying to evaluate. And this is now the partial result that we are getting based on our computation in the previous page. What we can do now here is apply the sum law of the limit. Using now the sum law of limits, we can rewrite the limit of the sum of functions into the sum of the individual limits. In other words, I can evaluate the limit of the first term, evaluate the limit of the second term until the succeeding terms, and then sum up those individual limits. They are equivalent to the given limit here. So the result would now be like this. The limit of 1, n is approaching infinity. And then the limit of the second term, the limit of the third term, the limit of the fourth term, and so on. Remember, this is an infinite sum as indicated by this ... So we are not stopping only at these terms. So what's the limit of 1 as n approaches infinity? Since there is no variable, the limit here is the constant 1. The same here, the limit is the constant 1. But here, this n would approach infinity. So this becomes a very, very big number. So 1 divided by a very, very big number, the result is approaching 0. So basically this is 0. So what we have therefore is 1 over 2 factorial times 1 minus 0, which is 1. The same reasoning here, you have 1 over 3 factorial. This part here becomes 0 when n approaches infinity. This part here also becomes 0 when n approaches infinity. So you have 1 times this 1, which is still 1. So 1 times 1 over 3 factorial is simply 1 over 3 factorial plus ... And the pattern continues. You will have here 1 over 4 factorial, 1 over 5 factorial, and so on. So you have 3, 2, notice that this one can also be written as 1 over 1 factorial, and this other one can also be written as 1 over 0 factorial. Because 0 factorial is 1, 1 over 1 is 1. Because 1 factorial is 1, 1 over 1 is 1. So you now completed the pattern. You have 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on. And another way of writing this in mathematical notation is that is equal to the sum of the expression 1 over n factorial, where this n starts with 0, so n is from 0, and then iterate by adding 1, 2, 3, 4, and so on, and it will stop at n. But since n is approaching infinity, then this part here would be infinity. And notice that this part now here is what we have here. That is exactly what we are trying to prove. So at this point, we have just proven mathematically that the limit of this expression that Jacob Bernoulli discovered to be the value of E is equivalent to this expression that was used by Leonhard Euler when he computed efficiently the value of E up to the first 23 decimal digits using the crude technology available in 1600s. So you might be asking, what's so important about this formula? Now, let me demonstrate that to you. Notice that n could be any counting number from 1 up to infinity. Let's just choose some convenient number, let's say 7. This is just any number that we compute. You can select 10, 20, 30, or any number you like. For our example, I'm choosing 7. If n is 7, then we can expand this as 1 over 0 factorial, 1 over 1 factorial, up to 1 over 7 factorial. And using the calculator, its value is this, 2.7182, and so on. And notice that this part here, 2.7182, is a correct approximation of the number E up to the 4 decimal digits. And there is some variation here. Now, if you're going to compute for the value of E, the true value of E would be this value plus those other values that we did not include. Because we did not include 1 over 8 factorial up to 1 over infinity factorial, where infinity is not a number, it's just a way for us to say it's a very, very big number. If we are going to include all of this, then that would be the exact or the true value of e. But since we omitted all those other terms, then these other terms would comprise our error. So this is our estimate, and the other terms that are not included would be our error. But how big is this error? So our estimate now for e is this value. Our error then would be starting from 1 over 8 factorial plus 1 over 9 factorial and so on. So this would be our error. But this is infinite, so we cannot exactly know what's the value of this. But we can use some mathematical reasoning to quantify the value of this. Notice that if you have 1 over 8 factorial, 1 over 9 factorial, 1 over 10 factorial, and so on, there's a common factor here. The common factor is 1 over 7 factorial. Notice that 1 over 8 factorial can be written as 1 over 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But from here, going to that part, that is 7 factorial. So if I factor out 1 over 7 factorial, then what's left is 1 over 8. You have here 1 over 8. For 1 over 9, I have to include 9 here. So that means if I factor out 1 over 7 factorial, I'm left with 1 times 8 times 9. For 1 over 10, it's the same thing, 8 times 9 times 10, plus, and so on. So we have now an exact value, 1 over 7 factorial, that we can factor out, and these terms would be the other factor, but still infinite. Now, recall the geometric sequence, 1/2 plus 1/4 plus 1 over 8 plus 1 over 16 plus 132, and so on. So the sum of this series is 1. Why is that important? Notice that if I have 1 over 8, and 1/2, if I compare 1/2 and 1 over 8, 1 over 8 is smaller than 1/2. This is small. 1 over 8 times 9, which is 1 over 72, is definitely smaller than 1/4. So this again small. And the pattern is term by term, these terms are smaller than the corresponding terms at the upper right. So we know that the sum of this infinite series is smaller than the sum of this series, whose sum we already know to be 1. And since 1 is a convenient number for us to choose, 1 over 7 factorial times 1 is simply 1 over 7 factorial. So we can estimate that the error is 1 over 7 factorial because these other parts here has a value that we know is less than that series. So this value here must be less than 1. So we can now think of this 1 over 7 factorial as an upper bound for our error. We are sure that our error is lesser than this because our error here is smaller than this value. And what is the value of 1 over 7 factorial? We can compute for that. And so we are now mathematically sure here that even if we cannot compute the exact value of the error, we know that it will not pass through this 1 over 7 factorial if our estimate for e is this value. So let's write that cleanly in the next page. So we now say that we can choose any convenient value for n. If you choose 7, then this is our estimate for e. The value 1 over 7 factorial, this value, would be our upper bound for error. So the discrepancy between the true value of e minus our estimate, which in this case is this value, would be the error. And that error is approximately this value. And so our estimate and the error would give us an approximate value of e, which at this point is not correct because we just chose a convenient number 7. But if we choose n to be a very big number that we can manage to compute, when I say big number that we can manage to compute, using our supercomputers now, we can compute the value of e to millions of decimal digits by just changing the value of n. In fact, if you let this n to be 205, that means you are going to compute for the error 1 over 205 factorial. That's a very, very small number. Then the first million digits of the expansion of this would be zeros, and therefore we can now compute the value of e from 1 over 0 factorial, 1 over 1 factorial, up to 1 over 205 factorial, and that gives us a precision for the value of e up to 1 million digits. So that's how mathematicians think. Something that seems impossible, they'll be able to find ways they can convincingly prove that the value they arrive at is something that we can really rely on. That's mathematical thinking.